Welcome to the forces topic. The fundamental physical laws that allow us to understand and work with forces are Newton's laws. And Newton's laws form the foundation of a topic within physics called classical mechanics. So this series of videos will cover an overview of what Newton's laws allow us to explain, so what kinds of problems we can solve with them, as well as when they're valid, followed by a review of the laws themselves and their applications. So in the previous topic, in kinematics, we were interested in describing and predicting the path of objects without worrying about what was causing them to move in the first place. And now, in this topic, we're interested in the cause of the movement. So we're interested in forces and how forces work, which brings us to Newton's laws. So as I said, Newton's laws of motion and also his laws of universal gravitation, which we'll study later in this course, form the foundation of an area of physics called classical mechanics. And for those of you that are interested, I've included a short video describing the significance of Newton's contribution to our current understanding of the universe at the bottom of this page. But classical mechanics describes, in physical terms, the non-quantum mechanical low-energy particles in weak gravitational fields. What that means really is it describes the parts of the universe that we can see and interact with in general without too much trouble. So the laws set out in classical mechanics allow us to describe everything from basic motion, fluid flows, magnets, electromagnetism, right up to and including the movement and the interaction of stars within galaxies and galaxies in clusters of galaxies. So it's definitely well worth studying. And as I said, the bases, or one of the bases of this classical mechanics, are Newton's three laws of motion. So these are they. We have the law of inertia, the law of acceleration, which is sometimes also known as the law of momentum, and the law of equal and opposite action. We'll look at each of these laws in detail over the next few videos, but before we do that, it's important to know the limitations on these laws, so when they're valid. And it turns out there are three conditions on Newton's laws. So the first is that we must be operating in the right size and speed range. And that range is, if you think about it, the range that was available in Newton's time for him to work with. So they had microscopes and they had telescopes. So we're kind of looking in that general size range. So essentially everything larger than an atomic scale. And when we talk about slow speeds, we're talking about non-relativistic speeds. So that's everything up to roughly half the speed of light. The second condition is that the objects must be particle-like. That means they must have mass. And the third and final condition, as the observant of you may have noticed, is that the object must be in an inertial reference frame. So in physics, if you have an observer watching your scene, the reference frame is what's happening to that observer. So if the observer is stationary, you have a stationary reference frame. Likewise, if the observer is moving with a constant velocity, your reference frame is moving with a constant velocity. And in an inertial reference frame, we want the simplest laws of physics that we can have for that given situation. So the definition of an inertial reference frame is one in which the observer has no acceleration. So from the previous topic on motion, we know that acceleration is defined as the change in velocity over time, or the rate of change of velocity. And that means, since velocity is a vector, it's either a change in the magnitude of velocity or in the direction of movement, as with circular motion. So that means for us to have no acceleration, our observer, or our reference frame, must be moving with rectilinear motion. So it must be moving in a straight line and at a constant velocity. So as an example, an interesting example, if we have a man standing on Earth and he's watching his friend run. So is that man in an inertial reference frame? Can he accurately describe the motion of his friend? So we know that he's standing on Earth, but we know that Earth is moving relative to the Sun. Yeah, it's circling the Sun, circular motion. And we know likewise that the Sun is moving relative to the Milky Way, and so on. And so each one of these things that we could possibly use is actually accelerating. And this brings us to an interesting point in that everything in the universe is accelerating. So we don't have the option for an absolute inertial reference frame. But the important point here is that the accelerations of these things, relative to what we're looking at, are relatively small. So although we can't find an absolute reference frame, inertial reference frame, we can find something, an approximation that's good enough. So now we know the conditions that we need to work with Newton's laws. In the next few videos, we'll start to look at the laws themselves.